Alright class, so what you have seen so far is to solve for the zero state response of the linear time invariant system. Um, the approach is to utilize the convolution integral, and we use the convolution uh, integral table in the textbook to in this example, and you're going to use this in your homework, in the exam, and so on. Now, you may want to ask if there are any other cases that the convolution integral will make sense. Well, the answer will be yes. But we do not go into the general case because that has very little to do with this particular class. If you go into the textbook, there's a particular section that telling you or teaching you how to use the graphical way to do the convolution integral. This is sort of all pure math. I will suggest encourage you to read that part, but I will not cover that in class, and you won't see anything like that in your exam as well. Okay. But if you look at the convolution table, you find the signals involved are all like our building block signals: u of t, delta of t, e of e, exponential signals, or some variations of exponential signals when you multiply t or t to the power n. Sometimes you see sinusoidal, but it's basically another version of exponential. The reason of that is because, as we discussed later, that almost all signals can be expressed sort of in terms of exponential signals. So that's why we only care about that. Second thing that you see in this table is you almost always have this u of t after each signal included in that table. That is because, first of all, most of the systems that we care about in this class are causal systems. And for causal system, your response, or your impulse response, h must appear after t equal to 0. So that's why you must have this u of t, corresponds to our observation 1. The second, the reason that you have this u of t, so many of them, is because, well, for linear time invariant system, the characteristic modes are in terms of e to the lambda t. And when you calculate h of t, and again, you're going to see this e to the lambda t because that's one of the first few steps you do in solving h of t. Then they will appear as well. That's why they call the characteristic modes or characteristic roots for the lambdas. So that's the reason we go through. We use the convolution table, and they can be very useful and commonly available to you when you do the calculation. Okay. Now, that being said, if we have more complicated scenarios, we'll have other tools that we can refer to, but that's not the scope of this particular section's discussion. Okay. Now, the last concept that we visited in the past video is the forced response and the natural response. Forced response is input induced, and the natural response comes from the characteristic modes. And although the example we have above is only the zero state response, we can expand that to the total response as well. So the total response of a linear time invariant system, combining what we have discussed, the zero input response, zero state response. Now, for the zero input response, it can only appear in the characteristic modes. The zero state response, some of them belong or appear in terms of the characteristic modes. Others will appear as the input induced terms. And when we talk about the total response, same notation. The characteristic response, the characteristic modes input induced ones will give us the ones called the forced response. In the convolution, right, in the convolution table, all the signals will have this u of t. That means the system is causal. H of t will have the u of t built in. It also means the input we consider will have u of t, or the input will appear only after t equals to 0. And this is natural because t of 0 is usually viewed as the point you start your observation. But there are other cases where you may have your input that look like an everlasting signal. It doesn't have this u of t. And that's what we're going to discuss next. So response of LTI system. To everlasting exponential signals. And this is also very important. Now ideally you can still use what we have discussed before, 0 state, 0 input, but since it's everlasting, will become slightly different. And the way to approach this is as follows. Notation-wise, let me use y total to denote the total response. So we'll decompose it into a natural response and a forced response. Y total and y forced. Okay? The way, just give them new notations. And remember the differential equation. Using this d polynomial or d operator and the pq polynomial. And plugging in this y total, y natural, y forced, what we have is qd y natural of t plus forced of t equal to pd. The p polynomial with the differentiation operator times f of t, your input. And f of t will be a everlasting signal that we'll discuss later. Now, what you'll find out is the following. When I further write down this equation, which will have this. And if you can think of this part, you may be able to figure out that this part will be 0. The reason it's going to be 0 is because the natural response will only have characteristic modes. And where did we see the characteristic modes in the first place? We saw them in the 0 input response. And where do we calculate the 0 input response? If I go back to the lecture notes, we'll be able to find out. Is right here. Which where I'm highlighting. Of course, this is a 0 input response, but why the 0 input response y here only also has the characteristic null. So it's not surprising that we have the same term here. And if we go back to our discussion, since natural response basically share the same terms, qualitatively speaking, we'll have a zero term. Or in other words, we'll only have to care about these. Or we can even make this simpler, right? We can make this look like y forced of t is equal to qd over, sorry, pd over qd times f. Sort of. I put in quotation mark here because we cannot directly dividing qd its differentiation. This gives us an idea how to approach this problem. And the way to approach this is the following. We're still going to focus on this equation, and we're only going to focus on one particular case, that f of t is everlasting exponential signals. So we will discuss in the following discussion that f of t is equal to, in mind that there's no u of t anymore, so it extends from t equal to negative infinity to t equal to plus infinity. Okay. Again, exponential signal. And of course, you should not use the convolution anymore because there's no u of t involved in this particular equation. So this input. Okay? So how do we solve this? And for this special case, what can we know about the forced response? We'll discuss this in Thursday's class.